Hi guys, hope all of us are doing great. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. Today we're going to look at the concept of conservation laws, and these laws basically are going to be analogous to the various discussion we have had on the concept of conservation of energy and other aspects that we're going to look at. So basically we're going to be biased under the aspect of radioactivity. As we say, the radioactivity is a mass transformation process. And in that specific respect, this concept of a relationship between mass and energy is going to be, of course, can be given using this specific relationship of energy mass relationship that was described by Albert Einstein. And this, of course, is going to give us a layer basis for us in trying to write various nuclear equations that we have discussed as an introduction as part of our radioactive decay process. So in this specific discussion, therefore, we're going to give a summary of some of the conservation laws that are going to be applicable in radioactivity. And this basically are going to be laws which are going to touch on a different aspect of the total energy of a system, the total energy or the total mass of a system that is going to be involved, linear momentum of that specific system, and the aspect of a charge of that specific system. And perhaps we're going to look at some of the areas that I've talked about, this aspect of angular momentum as well. So this is going to be an aspect that is going to be displayed in the aspect of a nuclear transformation, whereby it's going to involve energy mass, some aspect of momentum and the charge, as we're going to see. As we stated earlier that basically the nucleus is made up of two specific nucleons, which are the protons and neutrons, which have got different aspects of charges. Of course, we're going to see that this is going to be involved in the concept of charge, as I said. So basically, in trying to look at these various aspects that I've mentioned, they're going to assist us in trying to describe these specific conservation laws which are applicable in radioactivity. Now, as trying to achieve that, I'm going to use just a general example, which is, of course, is equivalent to a nuclear reaction that is going to assist us, of course, to describe this. Now, if we consider this specific reaction, nuclear reaction, general nuclear reaction, whereby we are having perhaps a specific nuclear reaction, whereby we're going to see X1 as perhaps a bombarding particle, and this is going to represent perhaps a target molecule, and then we're going to have products which are going to be formed as X3 plus X4. So as I've said, this is going to be what we refer to as a bombarding particle. So I'm trying to create a distinction between the chemical reaction and the nuclear reactions respectively. So in my general case, this is going to represent a nuclear reaction. So this is going to be a target atom, where perhaps we can take this one to be a helium nucleus that is bombarding this specific maybe nitrogen 14 etc. And we're going to have these specific products which are going to be formed after that one, perhaps a daughter nucleides and some of forms of energy which are going to be realized, and therefore these two are going to form a range of two, but not limited to two products. This one can form radioactive products, as we said. So if we try to perceive look at this specific nuclear equation in that specific format, we're going to see that we can be able to describe the total energy of the system, which can be illustrated as E1 plus E2, which is going to be equivalent to E3 plus E4, given generally as that. So if we try to describe energy in this specific aspect as a first part of that specific aspect, sorry for that, as a measurable property of this specific system that is we can be able to describe maybe perhaps as a physical system, then therefore we're going to see that the total energy of the system must be constant and therefore conserved, and that's going to form our first aspect of the conservation laws that we can be able to describe insofar as the nuclear reactions are concerned. If we consider the aspect of number 2 for linear momentum, now for conservation law that is going to entail the concept of linear momentum, we say that we can, from classical mechanics, we can be able to describe momentum as a product of mass and velocity. and therefore we can be able to describe this one as the momentum, the initial momentum is going to be equivalent to the sum of the final momentum that can be given as before, given as such. So therefore the momentum, the total momentum from in this specific system has got to be as well conserved. And I talked about the concept of charges. So if we try to look at the aspect of charges as well, we're going to see that the total charges of that specific system, which is a measurable physical quantity, then therefore is as well going to consist of number 3, the charge. And then a nucleus or an atom, we say that this is going to consist of protons plus electrons, which are positively and negatively charged respectively, as we are well known for this. So this is going to be conserved, and we can be able to, or rather it's going to be constant, and we can as well be able to give a summary of the conservation of charge using this just a simple equation that we have given for other systems of physical quantities, for the first two for energy and linear momentum as such. So this is going to be a charge that is going to be given in terms of electron units, or electron units that we had mentioned earlier. So if you try to also look at the concept of mass, we can be able to see that the mass is going to be the number of what we refer to as nucleons. Now we see that the electrons, of course, are consisting of we're not going to consider the mass of electrons, so we're going to consider the mass of protons and electrons in this specific nuclear reaction, and therefore the mass number, which is the mass of the nucleons in the system, must be constant. And we say that we can be able to represent mass number as that specific letter A. So therefore we're going to see that the mass number as well in this specific system is going to be conserved. So this specific arrow that I'm going to give, of course, is an equation and not a of course it's a transformation process, but we're going to see that as the particular physical system, as this specific system that consists of measurable properties of this specific system is going to evolve over time, but we're going to see that this aspect of conservation that we're talking for charge, mass, and perhaps angular and linear momentum are going to be conserved using these various equations that we're going to give in this specific aspect. So in that case, of course, we have looked at the charge, the mass number, which is number for nucleons, and also we can look at the aspect of linear momentum or angular momentum. But of course, it's going to be another physical, of course, measurable quantity that we're going to measurable property that we're going to see. And in this case, that we're going to see that also the total angular momentum of the system must be conserved, whereby we're going to have momentum given as this plus P1, 2 is going to be equivalent to P13 plus P14 given as such. So this angular momentum as well is going to be conserved in this specific system. And this laws for the total mass, linear momentum, total charge, and the angular and the mass number, of course, are going to be some of the conservation laws that we're going to see being applicable in most of the nuclear reaction. Now, this is going to be elaborate as we're going to do various reactions and try to see what are some of the nuclear equations that we're going to, of course, consider in that specific aspect, and also, of course, see how we can be able to give them. Now, we have given a general case for the nuclear the radioactive decay for specific emissions for alpha, beta, and gamma decay. And we're going to consider that some of the equations are going to consist of some of the symbols that we're going to see, of course, which are going also to assist in the process of stabilizing those specific products, whereby it's going to consist of perhaps antineutrino and neutrino and other aspects that we're going to see, which are, of course, we have not shown in our first case for the nuclear reactions in our first discussion. So I'm going to put a link of that specific video so that we can appreciate the concept of these conservation laws, which are going to come into play insofar as nuclear reactions are concerned. So that is it for now, guys. I hope that this is going to assist us appreciate the various transformations that we're going to encounter in some of the radioactive processes and the nuclear reactions, as we're going to, of course, do those specific reactions in terms of our quantities or quantifying them so that we can be able to appreciate the various aspects that we have discussed in totality, especially in the binding energy, the mass defect, and other some of the emissions that we have given as a summary of what I've shown at the lower part of our board, given as such. So that is it for now, guys. Bye. God bless.